Notation of hapticity, consider this structure M-phosphine. The ligand is p-phenyl-2, CH2, CH2, p-phenyl-2. So the ligand is DPPE, diphenylphosphine ethane. And this is a bidentate ligand. This is a bidentate ligand means it can be bound to M by one p center or from the two p centers. M-phosphine in this case is M-hap1 DPPE, since it's bound to one phosphorus atom. One phosphorus atom bound to the metal. So having a node hapticity in the non-carbon ligands of pi system does not mean that the ligand is anionic. If we have, for example, in the previous slides where we studied the bond between pi carbon atoms, we said hap1 means that the ligand is anionic. This is for the carbon of pi system. For systems that does not contain carbon of pi system, having odd hapticity does not mean that the ligand is anionic. It's, however, a 2-electron donor. So what to do is to write loose structure of this ligand and to see the charge and the donation. Note that many authors, especially the non-Americans, used kappa X instead of eta X when referring to non-carbon ligands. So M-hap1 DPPE is used by American. For non-Americans, they used M-kappa1 DPPE. In this structure, the titanium is bound to 4Cp, but the mode of binding is different. In the first, it's bound to one carbon of a pi system. So this is hap1Cp. In the second, it's bound to all atoms in the middle. So this is hap5Cp. Hap5Cp, and this is hap1Cp. So we have two ligands Cp hap1 and two ligands Cp hap5. In the second structure, this is hap2 diphenylphosphine ethane, or simply, if you want, you can write it kappa2. This is hap1 or kappa1 DPPE. Bridging ligands. For bridging ligands, we use the term μx, and this nomenclature is used to indicate the presence of a bridging ligand between two or more metal centers, and X refer to the number of metal centers being bridged to the ligand. Suppose you have a μ2, that means the ligand is bound to 2 metal centers. μ3, 3 metal center. μ4, the ligand is bound to 4 metal centers. And usually most authors omit X equal to when we say, for example, bridging. So at least we have 2 metal center. For this reason, some authors omit X2 and just use mu to indicate that the ligand is bridging the simplest case of 2 metals. Ordering of or listing of metal and ligands in the organometallic complexes. You know, for example, in organic chemistry, you have the Iupac rules to name hydrocarbons, and in organometallic we have also Iupac rules that should be followed by the organometallic chemist. Rule number 1: in a structure containing CP ligand, CP is written the first, followed by the metal center. For example, CP2 TiCl2, we have CP, so CP is written before the metal. After CP, other anionic multi-electron donating ligands are also often listed in front of the metal. For example, the tris pyrazolyl borate anion TP. So if you have CP, TP, and metal, the structure is written CP, TP, metal. In the rule number 3 for the metal hydrides, MH precede the metal center, but not the CP, it could not precede the CP or TP. For example, if you have CP, TP, H, and metal, you write by this way, CP, TP, H, then metal. The bridging ligands are usually placed next to the metal, cobalt MuCO, bridging ligand. After the bridging, we put the anionic ligand, then the neutral. So the general rule is CP, TP, H, metal, bridging, anionic, neutral. The geometry of the metal is very important to know the reactivity of this organometallic complex. And simply, we use the common structures, band, trigonal planar, tetrahedral, square planar, bipyramid triangle, or octahedral. Why the structure is very important? Suppose we want to add a ligand to this structure, and we have vacant site, but the presence of 6 ligands around the metal center will hide the open or the vacant site of M. So in this case, the external ligand L' could not be added, and this organometallic complex become inactive in our reaction. In this structure, we said we could not add a ligand L, for example, a ligand L', supposing that the structure is bulky. The number of ligands around M and the nature of this ligand, if bulky, will affect the presence of the active site or of the vacant site. So in this structure, we have a lot of ligands, and if the ligands is also bulky, so M could not add a ligand L' external. What to do? The structure of ML5 may be changed internal rearrangement to the structure ML5 where it's pyramid triangle. So the vacant site is clear now. Any ligand L' from this side will be bound to the metal M. For this reason, we have to know the geometry of the organometallic complex. By the same way, the square planar is ML4 and the tetrahedral is ML4. But the square planar is more active since the vacant site can be reached by another external ligand L' easily. This is the representation of p orbitals and d orbitals of a metal center, and as I said, we have for a metal center, we have practically orbitals in all directions. The strength of a chemical bond is related to the amount of overlap between the atomic orbitals of the two atoms. Consider the examples of C double bond C and Si double bond Si. The amount of overlap between orbital of carbon and second orbital of carbon, the green areas, between the p orbitals is small relative to the part in yellow that does not overlap. By the same way, in case of Si, the green part, which is the overlap between orbitals, is small relative to the green or the parts that do not overlap. So by theory, C double bond C and Si double bond Si are not stable, are not strong. If we compare C double bond C and Si double bond Si, we observe that Si double bond Si is weaker, since the overlap efficiency that can be thought as the orbital overlap area divided by the non-overlapping area. In case of Si double bond Si, the overlap efficiency is smaller. So the smaller this ratio, the weaker the bond. In organometallic chemistry, we think by the same method, by the same strategy. When we have M and L, M has the orbitals and L has orbitals. When the overlap between M and L orbitals increase, the bond is stronger. And if we compare, for example, the sigma bond Ml and the pi bond Ml, for sigma bond, the efficiency is close to 1, so 100% overlap. So the sigma bond Ml is stronger than the pi bond Ml. The electron counting in organometallic chemistry is very important to predict the property of the compound, of the complex. If the organometallic complex is saturated, so in general, it cannot act as a catalyst. In organic chemistry, the compounds follow the octet rule because we have orbitals and S and P completely filled. In transition metal and due to the presence of d orbitals, we extend the octet rule to the rule of 18 electrons. The bond Ml or Mx can be drawn in organometallic chemistry by two models. Model 1, which is the Ionic model, so we suppose that Mx is equivalent to M plus and X minus, and we have the covalent model where the bond between M and X can be drawn as sharing of electrons. And in general, we prefer the Ionic model. How to count the electrons in organometallic complex according to the Ionic model? First, I advise to make a table where we have ligand, charge, and donation. For example, I have NH3 if you don't know the charge, draw Lewis structure as usual. So the structure is saturated, the charge is 0, and H3 is neutral, and is 2 electron donor by the lone pair of N. Suppose I have, for example, CO. We draw the Lewis structure of CO. Okay, so CO is a neutral and is 2 electron donor by the lone pair of carbon. Suppose we have ethene. We know that ethene is a neutral and 2 electron donor by the p orbitals of carbons, so it's 2 electron donor. So first we construct this table, charge and donation of the ligand. Second, determine the oxidation state of the transition metals, and pay attention that the sum of the oxidation states is equal to the charge of the complex. Suppose we have, for example, platinum, Cl2, NH3, 2. So the oxidation state X plus 2Cl minus 2 minus 1 plus 2 NH3. NH3, the sum of the oxidation state is 0, is equal to the charge of the complex is equal to 0. So in this case, X equal 2. Okay? We write the electronic configuration of platinum. Then platinum 2 is platinum minus 2 electrons. Then we count the total number of electrons. The platinum 0 is D8, is D8S2, so platinum 0 is D10, S2 D8, so platinum 2 is D8. We have platinum 2 8 electrons, 2Cl minus, so 2 times 2 equal 4, 2 NH3, so 2 times 2 equal 4, so the complex is 16 electrons. By the same way, we'll treat this complex. We have W methyl. What is the charge of methyl? Methyl is CH3, so the charge is 1 minus and is 2 electron donor. So W in this case is W X plus 6 times minus 1 equals 0. So the oxidation state is W6. W6, W is W0 is D6. So W6 is D0. So 0 electron from W plus 6 ligands, each is donor of 2 electrons. So the complex is 12 electrons. Counting, we can use the covalent model. In the covalent model, if we have, for example, Mx, in this case, as X is donor 1 electron, and if L is bound to M by a lone pair, L is donor 2 electrons. we have to follow also the rules. Rule number 1, we consider the metal and all ligands have oxidation state 0. So we consider the ligand is free and the metal is free. Add the valence electrons of the metal and the electrons donating by ligands. If you have a metal-metal bond, you count 1 electron for each metal. If you have double bond, you count 2 electrons for each metal. And the charge limit on the complex is also count. If the complex is charged negatively, so you have to remove electrons. And if the complex is cationic, charged positively, you add electrons to the total number of electrons. I will treat this example. This is zirconium zirconium 0. Zirconium 0 means D4. I have CP and CP. The CP in the ionic model is 6 electron donor, but in the covalent model, CP minus, so 2 electrons and 1, so CP is 5 electron donor in the covalent. Cl is 1 electron donor. So in this case, we have 4 electrons from zirconium 0. We have 2Cl, so we have 2 electrons. We have 2Cp, implies 2 times 5 equal 10 electrons. So the complex 10 plus 2 plus 4, the complex is 16 electrons. Consider the complex of rhodium. Rhodium 0 is D9, implies 9 electrons. We have 3 phosphines that are bound by the lone pair, so p-phenyl 3 implies we have 3 times 2 equals 6 electrons, and we have 1 Cl, so 1 electron. The total is 1 plus 6, we have 7 plus 9, so the complex is 16 electrons. But as I said, we prefer to use the ionic model. Please count the electrons in this complex by the 2 models, the ionic and the covalent models, and you have the solutions. The main important part, or the main important point, is to know the charge and the donation of the ligand. Any error in the charge or the donation of the ligand, so the oxidation state is not correct and the electronic counting in the complex is incorrect, so it will change all the properties of this complex. In this table, we have the common ligands for the formal charge and the donation. In some cases, we have several types of donation. We have the ligand 2 or 4 or 6 electron donor. So we use the common one, which is the simplest, which is the first. Okay. And how to know the charge and the donation? If you don't know the charge and the donation, please write Lewis structure. If the structure is saturated, so the charge of the ligand is 0. If not, you search how many electrons do you need to have saturated structure, and then you can know the charge and the donation of this ligand. You have to read these tables. I will consider this example. Oxide O2 minus. O2 minus, since it's double minus, so we start to say it's for electron donor. Minus 2, charge minus 2 is directly for electron donor. It may be 6, but this is a rare case. So O2 minus is dianionic for electron donor. And we will consider all these ligands in the corresponding chapters. We will study the charge and the donation in each chapter. I explain some donation of alkenes, of benzene, of cyclopentadienyl. I explained before. And I explained the hapto 1, hapto 3, hapto 5. What are the common ligands used? We have cationic ligand to electron donor as nitrosyl. We have neutral ligands to electron donor as phosphines, carbonyl, alkene, nitriles. We have anionic ligands to electron donor as halides, methyl, alkyl, phenyl hydride. Some of these ligands may donate 4 electrons if needed. We will see in the examples. We have anionic 4 electron donors as allyl oxides, sulfides, imido, alkylidine, and we have anionic 6 electron donor as nitride N3-, so we have N triple bond with the metal, and as cyclopentadienyl Cp-. Counting example. In the first, we have Re center. First of all, we make the table ligand, charge, and donation. CH3 is 1-, 2 electron donor. CO is a neutral, 2 electron donor. PR3 is a neutral, 2 electron donor. Alkene is a neutral, 2 electron donor. If you know directly the charge and the donation of the ligand, you write it. If no, you have to write Lewis structure for the ligand so you can know the charge and the donation. Second, we find the oxidation state of the metallic center. X plus 2CO 2 times 0 plus 2 phosphine 2 times 0 plus 1 alkene 1 times 0 plus 1 methyl, 1 minus, is equal to the charge of the complex, and the complex is neutral, so equal 0. In this case, X equal 1, and we have Re 1. Re0 is, according to the periodic table, is D7. So Re1, D6, so we have 6 electrons. One CH3 minus will put the charge, so 1 times 2 equal 2 electrons. We have 2 CO, 2 times 2 equal 4 electrons, and we have 2 phosphine PR3, so 2 times 2 equal 4. So as a total number of electrons, we have 6, 8, 12, 16 electrons. Example, we have a complex of molybdenum and we have CH3CN ligand. Suppose we don't know the charge and the donation of CH3CN ligand. So we write Lewis structure. Valence electrons, 4 for carbon, 3 times 1 for hydrogens, plus 4 for carbon, plus 5 for nitrogen. So 9, 3, 12, so we have 16 electrons. We have C, N, and the 3 hydrogens. So we distribute 2, 4, 6, 8, 10, minus 16, so we have 6 electrons remained. We put it on the outer atoms. We look to the structure. This carbon does not have orbital completely filled, so we transform the lone pair of nitrogen to nitrogen to a bond on C. Okay, so this is the structure of acetonitrile. The structure is saturated, is complete, so CH3CN is a neutral. We don't have to add or to remove the electrons, and is 2 electron donor from nitrogen. Is 2 electron donor from nitrogen. So MO, we return to the example, we find the oxidation state of MO plus 2, 4, 6, 2, 4, 6, 7, plus 7 times 0 equal 2. So X equal 2, and we have MO2. MO0 is D6. So MO2 is D4, 4 electron, and we have 7 acetonitrile, so 7 times 2 equal 14, and the complex is 18 electron complex. The charge and the donation of this ligand attached to M. First of all, We have to break the bond. So we have CH2, R2P, CH2. So the carbon has 2 bonds with hydrogen and 1 bond with phosphorus. So it should be CH2 minus to have orbitals completely filled, according to Lewis structure. By the same way, CH2 is CH2 minus. So this is equivalent to CH3 minus CH3 minus. 2 bonds with carbon and 1 bond with P, so it behaves as CH3 minus, or simply Cr3 minus, where we have R equal 2 hydrogens plus 1 phosphorus. So till now the total charge of the ligand is 2 minus. But look to the phosphorus. The phosphorus in this case is R2P, bond with carbon L, and bond with carbon L. So it's equivalent to R4P, and this is a phosphonium. So we have a plus on phosphorus. Totally, the ligand charge is 2 minus plus 1 plus, so is 1 minus. This ligand is anionic, 1 minus, but 4 electrons donor, 2 electrons to each M. Example, we construct the table, ligand, charge, and donation. So we have a ligand, charge, and donation. From this side, this is a diphosphine. The charge, so it behaves as PR3 and PR3. Diphosphine is equal to 2 PR3. The charge is 0, and the diphosphine is 4 electrons donor. We have CO, the charge is 0, 2 electron donor, and we have bridging Cl. The bridging Cl has a charge, as we said, a charge 1 minus, and is 2 electron donor to M. I'm working on the first metal center since the structure is symmetrical. Calculation the oxidation state. We have 2 molybdenum, so 2X, plus 2 phosphines, 2 times 0, plus 4CO, 4 times 0, plus 2Cl, 2 times minus 1, is equal to the charge of the complex is equal to 0. So MO 2x equal 2, so we have MO 1. We can work on the 2 metal center, or we can work on 1 metal center. If you work on 1 metal center, the charge of this Cl is minus half, because the charge is distributed on 2 MO. So if you work on 1 metal center, you have to count the charge of Cl minus half and the charge of the second Cl minus half. So totally, the charge of the 2 bridging to 1 MO is 1 minus. But it's better to work on the total complex on the 2 metal center. MO 0 is D6. So MO1, T5, 5 electron. We have 1 diphosphine. So we have 1 times 4, 4 electrons. We have 2 CO on metal. So 2 times 2 equal 4 electron. And we have 2 mu Cl minus. HCl is 2 electron donor to MO, so 2 times 2 equal 4 electrons. And we have 1 metal bond, which is count 1 electron for each center, MO, so it's 1 electron. As total electrons, we have 5, 4, 9, 13, 17. So this is a complex of 18 electrons.